So we came to that definition of an improper integral where the integral goes from the interval of integration goes from minus infinity to infinity, right? And the real definition of that, so this is just sort of like an indication, but really that means the work of two separate improper integrals as one from minus infinity to a, right? And that's from a to positive infinity. And so in that way right here, let's look at an example. The integral from minus infinity to infinity of x to the fifth e to the minus x to the sixth dx. And so when we start into this problem right here, it just means, so when we see this symbol, it just means that we can think in the back of your mind that there are two integrals, and the number that we pick here can go arbitrary. We can think about an integral from minus infinity to 0 over here. So that can represent the sum of some integral from minus infinity to 0 and another integral from 0 to positive infinity. So anytime you see this symbol, it means two separate integrals, right? And then if for any reason that these two both converge, and go to some finite value, then we can add them up. And that's why we just start out with setting up the work like that. X to the fifth e to the minus x to the 6th dx here. Okay, so that's the starting point because this is defined, right? That equality right there means it's defined as two separate integrals. And so, before we go too far here, I keep having students question in my past quarter question me, does it have to be 0? Like this 0 here and that 0 there, then it doesn't have to be 0. You can just basically think about any arbitrary finite, any arbitrary actual number, fixed number here. So you can choose -1 here as well. You can choose a positive 2 here as well. But the point is that these two numbers must be the same number here. Okay. So it does not need to be 0. Okay. And then choosing 0 is usually making it, the best. That's all. And then we can double confirm that our function overall here is continuous throughout the whole real number. The side note here, x to the fifth e to the minus x to the 6th here is continuous in the whole real number. Okay. And so now once we realize this, then we've got two separate works, right? So this work right here, and we've got quite a few different ways of organizing it. You can also think about considering one separate work. So this first term right here, think of that as some integral, right? From when you're letting it s, right, going to negative infinity, it's an integral from a finite integral from s to 0, right? X to the fifth times e to the minus x to the 6th dx, right? So with something like this, we can easily get we can go with the substitution method here. Getting u equals x to the minus x to the 6th power right there. Okay. Then yes, that means that u dx equals minus 6 x to the 5th. So that leads to du over minus 6x to the 5th, right? Where e equals dx. Okay. So after rearranging the differential, so this integral here will become, we have the limits, s go to minus infinity, and then keep in mind further when u equals x and we minus x to the 6th right here, you got the u1 right here, right? Substituting 0 into your, substituting s into your function, you got minus s to the 6th, right? And then u2, which is the high, it's going to be a 0 because it's 0 to the 6th, which is 0. So your integral here can easily become integral from down here we got the minus, right? S to the 6th. Here we got to 0, right? Here your function goes up x to the 5th times the e to the u, and then all of that dx right here is substituted by du over minus 6x to the 5th here. So just like usual, the x to the fifth got canceled, right? We got negative 1 6. We put outside, so it becomes the limits for s to negative infinity. Here it's minus, and actually there's a minus now. Should have written that here. Right? It's a minus 1 6, right? And then from minus s to the 6 to 0, yeah. Right? And then your function is e to the u, du. Okay. So with this one right here, the integral becomes quite straightforward right here. It's still a limit problem, right? S going to negative infinity, and then it's minus 1 6, e to the u, substituting in, rather substituting minus s to the 6 and 0. Any question for me so far? And I'm going along. So here, I'm looking at minus, that's more space for myself here. So minus 1 6, right? E to the 0. And then I'm subtracting, and then subtracting a negative 1 6 is making it plus, right? So plus of 1 6, right? E to the minus s to the 6 power. And then all of this here, I'm going to take the limits as s approaching negative infinity. You guys clear that still? And so for this particular problem right here, think about it. Now, this term, when we're taking this limit, now when s is going to negative infinity, and you notice up to this point that this expression is entirely in terms of s, right? And so this first term here stays constant, negative 1 6, but this second term here, as you take limits for s going to negative infinity, think about it. Well, you can rewrite this. You can also rewrite this as a 1 6, right? Times 1 over e to the s to the 6 power. That's quite an awkward way of writing that. So 1 over 6 e to the s to the 6 power. Okay. Now s go to negative infinity admittedly. And back in Cal 1, right, when I was teaching Cal 1 and you guys can remember that when we were doing this in Cal 1, when it's to negative infinity, we can sort of like change that to a temporary variable. Remember that the substitution, that quick little substitution right here. So I'm going to just let the s right here with the minus z right here. Right. And so it be like that. And so the problem here becomes really the limits, right, for z to the positive infinity. And then your expression here goes negative 1 6, right? E to the 0 is a 1, and then plus. Now that expression here is really just 1 over e to the minus z all to the 6. But minus z is all to the 6 is even power here, right? So it's all making it positive z to the 6 here. That's why this whole term here, right, will bunch to 0 then, right? So your final answer here is a negative 1 6, which is a finite number. And so you got a convergent one. You got a convergent one. But sadly, this is only half of the work, right? It's only half of the work. Yes, so these limits right here, it's not hard, but it's just taking some time to get. Okay? It's just a little bit of time consuming. So you got one limit, the convergent. Right? You got a finite limit, but don't forget, you still have to do the other piece of limits, right? And only both of them, only both of these two separate works right here coming out with a finite limit. Then we can say that overall integral will converge or come to a finite limit. And so in that case, I'm going to consider the other one again. So I'll have to leave that definition here for us. The other one, we got x to the fifth, right? E to the minus x to the 6. We're going from, right? We can produce limits for t going to infinity. But now we go from 0 to t. Look at that still. The x, right? So again, I'm going to do a little substitution rule over here for this. Easy enough. You see, I mean, everything is pretty much exactly the same with that. So I'm going to say similar substitution. Okay. And let u equals to that minus x to the 6, right? And so your problem will turn into, right, will become a limit t is going to positive infinity, and then your integral goes to minus, right? And here we have 0, but 2 minus t to the 6th power. That's how it happens, right? Your integral goes x to the 5th times e to the u, minus u over minus 6 x to the that minus 5th power. That's why the next step cancels out the x to the 5th here, that limits t on infinity, and then minus 1/6. The integral will go from 0 to minus t to the 6, e to the u. So the integral will come into the still limit problem, t to infinity, minus 1/6, and u. We're evaluating that from 0 to minus t to the 6. Okay. So I have that come out as a limit from positive infinity, then minus 1/6, e to the minus t to the 6, then plus 1/6, e to the 0, which is 1 eventually. Okay. So the very similar argument, and here it saves us from that headache about substituting the variables or turning to the opposite variable, right? So now we can just simply see this as the final limit here being a negative 1/6 as well. So it's also a convergent one for us, right? So we're having the two convergent ones. Then you can say that the final, after considering the two separate ones, the final integral minus infinity to infinity on this function here, x to the 5th times e to the minus x to the 6th, dx will equal negative 1/6, plus another negative 1/6, negative 1/3. Right. So that's how we solve that problem. And so when this final, so when both of the, see, in this particular example I brought up right here, the one that goes from 0 to t, right, converges, as well as the other one that we worked previously. This other one that's going from some s to 0, right? These two pieces, they're both convergent here. And so your final integral here, this one here, you're going to say it's a convergent as well. Right? Any question for me? You're right. For some reason, I keep thinking this gives me that negative. You're right. It should be just positive 1/6 right here. Does that go to 0? Right? Yeah, you're right. That's positive 1/6. Okay. Now you got negative 1/6 from previous work, and plus a positive 1/6. Now we're adding that together, we come to 0. Right? But that's making it still a convergent final integral. So this, back to this definition, I purposely left some space right here. So we're going to say that the integral from minus infinity to infinity f of x, right? Dx here is said to be convergent, right? Both of those converge. Then divergence. So that same integral right there is said to be divergent, right? Okay. Otherwise. So when I say otherwise, it just means as long as one of these fails here, right? As long as one of these two integrals that primarily built our overall infinite integral, one of those fails, right? To be convergent or divergent, and any one of these diverges, okay? The whole integral itself diverges. Right? going along this property here, you guys can help me with some part of it, that be better. So the interval we have here is minus infinity to infinity. We got e to the minus 5x dx here. Go ahead, spend some time writing it down. So again, when we see this notation, right, it just means we have two separate words, right? That's why by definition, we're going to have to produce one word here is going from minus infinity to 0, right? And 0 doesn't have to be the only choice you can go with, also 1, right? But a lot of times 0 is easiest. So we got one improper integral from minus infinity to 0, e to the minus 5x dx. We're going to add that result if that one exists, right? We're going to also need to find another one from 0 to positive infinity, e to the minus 5x. Think about these two separate integrals again. Find them, right? And then we're going to add them together to get that answer. That's how it's defined. Right? It's defined as just two separate integrals added up. So in this case, let's look at this first one right here. Right? The one from minus infinity to 0, right? E to the minus 5x dx. Well, by definition, that means it's a limits problem. We're going from some s, right, to 0 over here. We're letting s approaching negative infinity. Right? E to the minus 5x dx. And this integral here is quite simple, so I can go, it's going to get negative 1/5 e to the minus 5x, right? That's the antiderivative. We're evaluating that from s to 0 over here. Those limits for s minus infinity. From s with negative infinity, and negative 1/5 e to the 0 with them, right? And then plus 1/5 e to the minus 5s. And then think about doing that substitution with this. Now it's an expression completely in terms of s. And we're letting s go to negative infinity. So think about we're going to let s to equal negative z. For this case, so that's turning it to meet z going to positive infinity. And our function here is negative 1/5. And by the way, e to the 0 is just 1. Right? That's why I'm writing it like that. And plus 1/5 e to the minus. Actually, now it's turning to a positive 5z here. Right? We'll change that. But then this case right here, this term stays constant, but that term grows to positive infinity. Right? It grows bigger and bigger because the z now is a positive z. You guys follow that together? Right? And so now in that case, here we're looking at this one here, this particular one, divergence. Right? The answer comes out positive infinity. So that leads to this integral here from minus infinity to infinity. To 0, e to the minus 5x. This one here, diverges. So now, as long as you find one of these two guys, right, diverges, then you don't need to evaluate the other ones. Now, if as a matter of fact, there was no strict rule about you have to start out with that first, or you started with the other one first. See what I'm saying now? So in some other cases, if you're starting out with one piece being convergent, you still have to make sure you test the other piece. See what I'm saying now? Okay. So make sure you test both pieces to ensure that they are both convergent in order to say the final one is convergent. But in this case, we just whatever by a random choice again, right? Our first piece here fails to converge. Okay, it's already a divergent one, so there's no need to test the other ones. You guys follow what I'm trying to explain with that. So now our final integral, you can just say the final integral from minus infinity to infinity, right? E to the minus 5x. This integral here, divergent. Right? So we learn to evaluate that, but along the way the evaluation process, right, helped us determine whether the integral, the improper integral diverges or converge. Right? And so at the end, we've done. If you guys go back to these, pretty much the same definition, but I extended that to three separate sub-definitions, right? It's, remember the definition A, definition C, definition D and C and so on. So we are currently at definition C right here. Why don't you guys go back to this beginning one and the whole time so far? This definition, let's just say that this is a, let's call it, this is a type 1. Right? This is a type 1. So here's what I mean by type 1 right here. It's throughout, the A, B, and C so far. It's a definition for the type 1 improper integral. That's precisely speaking. Because here, I started out with this problem, if I remember. At least we defined, right? We defined this one right here. An integral from A to infinity of the function, right? So this integral right here, what we noticed is the integration interval was an infinite interval. We got an infinite interval. You guys follow it? So one side of that is an infinite interval, right? The other side is fixed, and the upper side is infinite. That's why this integral, this improper integral we introduced in part A right now of the definition belongs to this category, that criteria. And then in part B, we define this thing right here. From minus infinity right, to A. It was another infinite interval. And interval here, I mean the interval integration. So that was what we've done in part A and part B of the definition. And then just now, part C is still on the board here in front of you guys. We're looking at is an integral from minus infinity to positive infinity. This is like a total, complete infinite interval right here, right? So f of x, right? Dx here. Yep. Another infinite interval here. So all of these, so the whole definition so far, part A, part B, and part C, all refer to those different cases of some infinite interval being involved together, right? Either a total infinite interval or two-sided infinite interval together. And that's why this kind of integral, this kind of improper integral, that many textbook authors and many professors, including me, here refer to this as the type 1, the improper. These are the improper integrals, right? Of type 1. See what I mean? Because there's another type waiting for us. Sounds good? Right? That's why now back in this definition right here, I want you guys to label that definition here as a type 1. It's a definition for those type 1 improper integrals. Any questions? All right, so now let's look at this problem right here. It seems nothing unusual at first, right? It looks like nothing unusual at first. At first sight, looking at this integral over here. But now we're treating that as an x to the negative 1/2 power. You guys agree? Right? And the integral goes like that, and then we go from 0 to 1, right? We'll be on that still. And then the fundamental theorem of calculus comes in and indicating that it will become x to the positive 1/2, right? And with a 2 in front. We good? Okay. And then we're evaluating that from 0 to 1 right there, right? And then we may got some kind of answer right here for that. We go with a 2 and minus 0, right? I'm skipping steps a little bit, right? And then we got a 2. Saying that? Okay. Now let me tell you that this answer is way out. That's incorrect. You guys see why? Now remember that major requirements about those integrals. Before we can even use the fundamental theorem of calculus, the function must be right. When we get into improper integral, we got to dive further into the fundamental theorem of calculus a little more. But the function must be continuous in the interval from 0 to 1, if we want to proceed with this result with the fundamental theorem of calculus. Right. But is it even continuous in that interval, including 0? It's not. Okay. The highlight is here. The problem here is f of x, right, is undefined. What I'm saying now, undefined, right, at x equals 0 here, which is right at that endpoint included in the interval, right? So the function, yes, the function is continuous everywhere. Now, developing this a little further, the function is continuous. The function is continuous anywhere in the interval from anywhere above 0 to 1. You see, this half open interval is different with that, right? With any value in there, the function is defined and continuous, but it's just not at 0. See that situation right there? Right. And so, with this problem right here, we really can't we can't rush directly into using the fundamental theorem of calculus. Major reason it fails being continuous at that endpoint where the fundamental theorem of calculus requires it's continuous throughout the whole interval, right, including the two endpoints. This function fails that. See what I'm saying? It's only continuous. It's only continuous in any square inside, but including the right side, yes, the upper end, yes, it's continuous there, but not on that low end. So the interval we have here is one side being discontinuous. It has a discontinuity. And so the way we handle this problem, here's how we're handling it. We're actually going to treat it like this. We're going to treat it as we're going to think about that as some integral from t to 1 right there, okay? Of the function 1 over square root of x. Then keep in mind that t is some value that's strictly greater than 0. And then yes, less than or equal 1. T is some value strictly greater than 0. Think about the interval of integration here, right? 0 to 1. We pick a t in here. We pick a t here and 1 here. So t is somewhere gotta be strictly greater than 0. That can be equal to 1. So when it's exactly equal to 1, we got accumulation being all 0 out, right? If we're talking about some t, so now t is making it finite. But then we're going to take the limits, allowing t to get to 0 from the right-hand side. Just think about, I'm going to move t right here closer. See, t is here. I'm not happy enough. I'm going to move t closer. I'm going to move t closer and move t closer to 0. But in that way, how I'm doing this, t is getting closer to 0 from the right-hand side. You guys following? So I agree. I admit that back in the days we've learned about calculus 1, right? The sided limits that we didn't do too much about. Because mostly we use that just to serve an overall limit here. But now when it gets to this, we actually dive much deeper into working with sided limits here. Here we've got those limits approaching 0, but from the right-hand side. Alright? Are we good with that? But then, of course, all the limit laws that we've learned back then in calculus 1 will hold here. We will work exactly the same. Right? So in this problem here, here's the way how I'm approaching it. Right? So I'll go. So now with this one right here, then we can guarantee that f of x, right, is continuous. T 1. See what I'm saying now? Or for any t value, right, greater than 0, but less than 1. Now that's why the integral here will become something like this. This limit problem would come out being t equals 0 from the right-hand side, then your integral t to 1. You can now treat that as a limit problem, right? Integral from t 1 to 0 from the right-hand side, right? Of x to the negative 1/2 power. And that's making it now limit problem where t going to 0 from the right-hand side again, right? Where we're looking at now adding 1 to that and divide by 1/2, so we've got the 2x to the 1/2 power, right? Evaluating from t to 1. So it will become limit problem, right? Where t goes to 0 from the right-hand side, right? And here we got a substituting it in according to the fundamental theorem of calculus. Now we got the 2, right? Because 1 substituted in the 1/2 power, it's going to be just 1, right? 1 times 2 minus the square root of t. And then now we're taking t go to 0 from the right-hand side. And this is making it legitimately, right, according to the limit laws, right? basic limit laws, 2 minus 1 root of 0, which is 2. Now, yes, we got an answer 2, just like that earlier, but that's with the proper process, okay, with the proper reasoning with that. It just happened to be the same right there. Even though we were doing the illegal work right here, okay? But you got to be extremely careful. See what I mean? So in this way right here, it came to a new definition for us. Okay, so if f of x is a function continuous on that half-open interval, then if that's so, the improper interval this improper interval right here, the interval from a to b, but keep in mind we can't substitute a into the function, right? That improper interval a to b, from a to b, okay? This function, this calculating this, the way we're doing that is defined to be the limit work on the interval from some s to b right here, when we're letting s approaching a on the right hand side, right, of that function. It turns into a decided limit like that. Okay. And of course, provided leave me some space here, I'm going to come back to doing some more, right? So just like that, we can also, the exact same function right here, right? If I can now ask you to be the same way, see? Now I can just simply look at the exact same function, but what about we take a different interval right here, integration interval. How about from, actually, it's not a good one for that, so how about x squared? Okay. And then from -2 to 0. Well, maybe -2 is a little too much, just go with -1. It's good enough. Okay. So let's look at that one. So in the way I see this, right, we can't just simply use the fundamental theorem of calculus. It looks at first sight looks very looks like just like any other usual integral, right? But then doing this with the fundamental theorem of calculus, we got x to the -1 power, right? And we're about to substitute -1, 0 right here. But what's wrong with substituting 0 right here? 1 over 0 minus a 1 over -1. You guys follow it? It fails right there as well. It fails with the fundamental theorem as well. Because the requirements here, in order to use the fundamental theorem, the function f of x, right, must be continuous in the interval from -1 to 0. But unfortunately, for this case right here, f is not, right? F of x right here is undefined. That's what we noticed. F is undefined at x equals 0 on the right hand side, the right end of that interval. Okay. And then so we observe further, we say, but wait a minute, for anywhere before, right, anywhere, see the interval is like this, from 0, from -1 is here, right, and then 0 is here, and anywhere before that, it's continuous, you know what I'm saying? No? So, in that way, I'm saying that, the observation is, right, but f of x, right, is continuous in the interval from -1 to 0, but half open. Sounds good? And then that right end right there is the open end. The open end. And so in that case, we can produce the following work here. Think about an interval from -1 to t here, right? And then we're letting t getting close to 0 from the left-hand side this time, right? Unlike that earlier work here, this time we're letting t approaching 0 from the left-hand side on our function, right? 1 over x squared dx here. And then, of course, for t value here anywhere greater than or equal to -1, but strictly less than 0. And so now things come out a lot more trivial over here. The fundamental theorem of calculus, because now t is, the function is for sure continuous in this interval from 1 over x squared as time, right? Will be continuous. It's continuous in the interval -1 t. See what I mean? That's why you can do the work easily. You can go the interval, right? Limits t go to 0 on the left-hand side, right? This interval, we can take 1 to t over x squared dx. That will become limits t go to 0 on the left-hand side. Right? But then it's going to be x to the, and by the way, it's a minus, right? Minus x to the minus 1 right there. Right? Evaluating that from -1 to t. So fundamental theorem of calculus stated that, and so we can further evaluate that as a limits problem. We're letting t go to 0 on the left-hand side. Here we're looking at minus 1 over t, right? And then minus a 1 altogether like that. Okay. So now for this function, the graph goes like this. You guys recall from your learning. No, it's minus 1 over t, right? So the graph goes like this. And so as t is getting to 0, t is on this axis, getting to 0 from the left-hand side, it rises to positive infinity. We look at that like that. Right? That's what happened with -1 over t. And so this term here goes to positive infinity and subtract 1. So the whole limits here turns into a negative infinity. I mean, no, positive infinity. See what I'm saying? No? And so we got some kind of answer, but that's the way how we're doing this. See what I mean? So sometimes, some other cases, some other problem, this limits may turn into a conversion value as well. Okay? But now, from that reason right there, we come up with a definition, another definition of how we're defining this kind of interval. So I'm going to call that part B of this example right here. Part B of this kind of definition. So I'm going to continue with that. The let f, right, be continuous. In part B, you can sort of like a different case, you get continuous on the interval from, right, on the interval from A to some B, but half over right, on the B end like that. If that's so, the improper interval from A to B, right, x dx will be defined to be, so that's what the equality here is going to define to be the limit process, right? Getting to B from the left-hand side of here, where we're taking interval from A to T, x dx, provided that's a finite value. Any questions for me on that? So let's look at an example right here. We're calling that example 3. We want to evaluate again, right? 0 to 1. So that one right here, see, obviously you can note that 1 over x, right, is only continuous on interval from. It's continuous at 1, but it's not continuous at 0. Got the idea? So that's why we got that half open interval like that, right? And so this fell right into that case A that we saw, that we've seen in the definition. So we can rewrite the integral. So this integral means the same as the limits work, right? For some s to 1 here, this function 1 over x dx, where we're letting s approaching 0 from the right-hand side. So now with this one right here, then and of course for here, right? F of x, I mean 1 over x is continuous, definitely. For s to 1, right? So that way I'm going to proceed here a little further. It's a limit process. S going to 0 from the right-hand side. The function here goes of what? 1. I mean, natural log of absolute value of x, right? And then we evaluated that from s to 1 there. And so it will turn out still a limit problem, right? Letting s to infinity, I mean to 0 from the right-hand side. Here we're looking at natural log of 1, right? Subtract natural log of s in absolute value. So natural log of 1 is a 0, so needless to say, in the next step, we're looking at just the limits, right? Or minus natural log of s in absolute value, where we're letting s approaching 0 from the right-hand side. We look at that. So what do you guys think this is? Well, the natural log function goes like this. So now if we, and this is our s-axis here, if s is getting close to 0 from the right-hand side, what's happening to the graph here, vertically? So it keeps dropping down, right, to negative infinity. But then in the end, indeed we got a negative sign with that, right? So the actual graph goes like this. The real graph that we're looking at goes like that. You want to say, huh? This graph right here is the graph for minus natural log of s. This one here is natural log of absolute value of s. Right? So here it goes to positive infinity as s gets closer to 0. So we got a divergence integral here. Right? So this integral here, I'm using the term. So this one right here, right? You know it's infinity, and say it's divergence. Right? So you can go back to this definition and kind of put in some wording on that. On any of these two cases here. Right? Set divergence. Writing it a little skippy here. This term right here we use for any one of the two cases here that we have for our improper integral. So in that way, let's look for another example of the integral from 0 to pi over 2. And our function gives simply tangent of x. Yeah. So as far as just the elementary technique, right? So you got to understand tangent here has a discontinuity at pi over 2. Tangent of x has a discontinuity, right? At x equals pi over 2. Remember the graph for tangent of x, okay? Tangent goes like this. There's a pi over 2 right here, and there's every jump of pi over 2. So there's pi, right? And then there's actually this one here is not asymptotic. Right? And then there's a 3 pi over 2. So your tangent goes like this. You guys still remember that? Okay, from trigonometry. Right? At least for one complete unit circle over here, with tangent made 2 periods, right, in your unit circle. And so pi over 2, we got the discontinuity. And so the interval of integration we go in here is from 0 to pi over 2, right? This is why you see things about we created an arbitrary area from 0 to some t, but letting t get close to pi over 2, right? Now realizing that, right? So we're using our integral as following. So that's integral of 0 to pi over 2 for tangent of x. Really, this is just the way we see that, but truly behind the scene, right? It's defined to be the limit for it. We're letting t get close to pi over 2, right? On the left-hand side, it's fine. Right? And then your function here, and your integral from 0 to t on the tangent of x dx. Right? Here we can do a little bit of scratch work because we have done the integral for tangent before. But in case you guys don't remember, we can do a quick scratch work right here, but we don't need to put that down as our formal work. So this is just scratch work right here, but just the antiderivative, just the indefinite integral for tangent, right? We can think of tangent of x right here as a sine over cosine. Remember that, huh? Okay. And so in that way, I'm gonna let u right here, right, to equal the cosine of x. So leading to u dx will equal minus sine of x. Okay. So the original differential, we're looking at du over minus sine of x, right? Will equals dx here. So we got every substitution that we need. Okay? So your integral here becomes a 1 over, let's formally write it like this, a sine of x, right, over a u and then times and dx is substituted by du over minus sine of x. So we're canceling out the sine of x, and then there's actually a minus sign right here. So the next term we're looking at integral from, or a du over u right here, which is minus natural log of of u plus c. Sounds good. And so we don't really need to plus c in a real situation of that definite integral. But keep in mind that u right here is cosine, right? So it's minus natural log, right? Absolute value of cosine of x, okay, plus c. So I'm going to bring this result and bring that into our problem. Okay. So the work here really turns out, right? After all of that explanation right here, now we got it's a limit problem where t is getting close to pi over 2, right, from the left-hand side. But our function, our antiderivative potential is now minus, right, natural log of cosine of x. We all did that. And then we substitute from 0 to t. Right? And then may I please erase this now? Right. This is just a reminder, and it should have been back in your notes, some of the early days. And by the way, back to this textbooks, actually bring that the minus sign in here, raise cosine to the reciprocal, so it's making it natural log, positive natural log of 1 over cosine there. That's why it's also, you see, secant of x there. That's another common way of writing that. Because this is the same as the minus sign right there means we're making that cosine of x to the negative 1 power. That's why it becomes a cosine, a secant of x. Yeah. But for this straightforward calculation, there's no need to get anywhere near that. All right. So we're going to go to the next step here. It's still a limit problem. But now we completely turn our problem into a limit problem here. And we're considering that left-hand side, what's t get close to pi over 2 from the left-hand side. You're looking at the minus, right, natural log of cosine of t. And now it's going to be a plus, right, natural log of cosine of 0. Is everybody following with me on that so far? Okay. Just simply substituting in the values again. And then the cosine, the plus right here came from because we're subtracting a minus. Okay. And then cosine of 0 is easy enough. It gives me, this is a 1, right? Cosine of 0 over here is a 1, but natural log of 1, the whole term over here becomes a 0. Everybody follow? So we have just simply a problem saying as follows. Limits, right? T going to pi over 2, right? From the left-hand side. But here we're looking at minus, right? Natural log of cosine of t, right? And then we're letting t comes to pi over 2. Good. Okay. And then so think about the logarithms function now. When t gets close to pi over 2, right, from the left-hand side and cosine, right? This is the same with logarithm itself right here is a continuous function. And so for that reason, it's the same as the limit log here, saying that we can take the logarithms, right, minus logarithm of limits for cosine of t, right, as t gets close to pi over 2, right, on the left-hand side. See what I'm saying now? But then as this happens right here, then what's going to happen to the cosine of t when t gets close to pi over 2? You guys remember? 0. Yeah, it comes to 0, right? But it comes to 0 here means what? On your natural log function goes like this. Your natural log function on the negative, right? The natural log goes like that when it's a negative. See what I'm saying? So as this inside the argument goes to 0, right? Your logarithm grows to positive infinity. See what I'm saying? So here we have another divergence, right? So this integral here, we came to an infinite limit. I'm saying that's our integral here is divergent. So we set out the calculation, and also we were able to determine that the integral was a divergent integral. Okay. So that's consistent with the way how we were saying that as a definition right here, that anytime the integral, right, is set to be convergent, anytime the limit exists as a finite number, but otherwise, right, in our case right here, it didn't exist as a finite number. The limit came out as an infinite limit, right? So our integral here is actually a divergent integral. Okay. And so let's look at another one. we have here is how about part C of the example? Yeah. Well, a minus 2, 14, right? 1 over 4th root of x plus 2. X. Go ahead, spend time writing it down. So this function 1 over the 4th root of x plus 2 is only continuous. It's another way how I'm saying it, only continuous on the interval anywhere strictly greater than minus 2, right? To 14 with that. See, the integration interval right here, the only problem is that that left end right here has a discontinuity. You know what I'm saying? Now that's why another way of saying it, the function is only continuous anywhere inside of it, except that left end point. That's why the integral here, now we realize it's an improper integral. Right? And so here, as a definition, this improper integral we're proceeding, x plus 2 here, dx, that is the same as doing a limit work. Here we're letting some s, right, going to negative 2, but from the right-hand side. Good. Here we go. S 14, right, 1 over what root of x plus 2 dx. All together still. Right. So this one here, the integral itself is simple enough. Think about, yes, you can do some scratch work here, right? When you take the integral for 4th root of x plus 2 dx here on scratch work, it gives you what? Well, you can do a quick little substitution. Right? U letting u equal x plus 2 here, right? So u will equals to dx, because it was du dx equals 1, and so I did, I found the derivative and I rearranged the differentials. Yeah. Now, integral here becomes a 1 over a 4th root of u du, right, which is essentially u to the negative 1/4 power. That's all. So that's making it easily a positive 4/3, right, times u to the 3/4 plus c, or as far as the integral itself, it's going to be a 4/3, right, times x plus 2 in quantity to the 3/4 power. So that's how we find our antiderivative, right? How we do that integral. So in this case right here, yes, limits problem. S goes to minus 2 on the right-hand side, and the integral now becomes a 4/3 of x plus 2 to the 3/4 power. We're evaluating this from s to 14. So something like this, right? Fundamental field of calculus, say we can go 4/3, right? Times now 14, substitute in, we got the 14 plus 2, which is the 16, right? The 16 takes the 4th root is a 2, am I correct? But, well, I can just all write it down as like that, 16 to the 3/4 power, and then you guys can use your calculator as well. But think about take the 4th root and then you raise it to another power. And then we're subtracting 4/3, right, times s plus 2. To the 3/4 power. And then overall, this is a limits problem, where we're letting s approaching -2, approaching the right-hand side. Okay. So you can double check my calculation, but this is the 4th root of 16 is going to give a 2 raised to the 3rd power is an 8, so 8 times 4 is a 32/3, right? And we're subtracting 4/3. S plus 2 to the 3/4 power. Now we take the limits one more time, showing the limits. Right. So now this is actually quite simple. This function here in the end, we're free from the denominator and all that, right? So when s gets close to 2 from either side, when s gets close to -2 from the right-hand side, or even from the left-hand side, this root nature right here is going to go to 0, right? And so that goes to 0, and then this now becomes just 32/3. Yeah, that's our answer. Okay. So in this case here, actually the integral itself turned into a finite limit, right? The integral was a limit prop, and the limit prop turned into a finite number. So now we say that the integral is a convergent integral. I'm saying that, right? Convergent integral. All right, so that's pretty much the consistent with the definition that was stated on the board there. Either one of the cases, right? Either one of the two cases for our integral with the discontinuity on one of the two ends here. Then anytime the integral comes to a limit, existing limit being a finite, right? We say it's a convergent one, and otherwise it's a divergent one. Right? And so now I have one last case to show everyone here. So let's look at a problem like this. And this is even more dangerous right here. Just so we got a 1 over square root of x, for example, dx. Now we want to take the integral from minus 1 to 1. And what I said earlier about the integral here being so dangerous, and really it's very dangerous because a lot of times we're gonna mistakenly do things like this. Well, we see that as a power net. A lot of people are doing this, right? X to the negative 1/2, right? See what I'm saying that? Okay, and then proceeding with that as the 2 times x to the positive 1/2 is adding 1 to that, right? Antiderivative and fundamental theorem of calculus, right? And then we're substituting in negative 1 with them. Actually, let me change the problem a little bit. How about change that to cube root here? That's the reason we can't substitute it in the negative 1 anyway. But so that's making it a 3/2 here, but multiplied with 2/3. This has no problem at all. Substituting it. Okay. And then the answer comes out in a number. So 3/2 times 1, right? And the minus, now it's 3/2 times, because it's 2/3 power, it's going to really just be a 1, right? And then here it's a negative 1 taken to 2/3 power. See what I mean? Right? And then it's all going to come out 0. Because taking the third root, it's going to be a negative 1, but then we square that. See what I'm saying? It's going to make it positive, right? But then in the end, somebody is going to mistakenly claim that this problem turns into a number. Sadly, it's wrong. Okay? You guys see why? Again, fundamental theorem of calculus only holds when your function is continuous throughout the whole integration interval. See, we keep digging further into the theoretical side of the fundamental theorem of calculus. Okay? But now, sadly, even before you use your fundamental theorem of calculus, right, it fails right there. We can't go this way, right? So the problem now is that this function 1 over cube root of x, right, has a discontinuity at x equals 0. So that x equals 0 falls right inside of your integration interval. And so in that case here, the way to work around with this problem here, we have to treat that as two separate. So think about it. If you have learned that skill enough, think about it. Think about a separate problem from minus 1 to 0 on this function, 1 over cube of x. That's completely doable for us, right? We can completely do something like this, like those among example 3 that we've just done with that. Because this one here is it's continuous on negative 1 and 0, but over there. Okay. So that was among those. I have a definition on the board with that. And then we can do a separate one, 1 over cube of x, our function. We can do the following one. We can from 0 to 1, right? This is also what we can do here. This function is continuous anywhere greater than 0 to 1. This is another case where the definition on this board right here allows us to do. So think about, hey, why don't we produce two separates? Think about two separates integral work, right? And then whatever the outcomes coming out from these two integrals, we can add them. You know what I'm saying, huh? Okay? We can add them. So we define this kind of work. We define this kind of work. So essentially, it's important to understand that these two are all limit work. They're two separate limits work. But we're adding the result of the two limits work. We define this work as, so if we define that as this integral over here, I think 1 to 1, right? Our function 1 over cube root of x dx. This equal sign doesn't mean really equal. It just means defined as, right? Defined as the sum of some two limit work, right? The sum of some two separate integrals. See what I mean? Right? And so in that case, I'm going to come back to this board here, and we're going to have to write down anything. Third definition. Okay, so the function f of x, right, is discontinuous. Some continuous at some x equals c, right? Or the c value being anywhere between a and b. Then in that case, right, the proper integral goes from a to b. Like right at first sight, it looks nothing unusual, right? But be aware that there's a discontinuity inside of your integration interval. That's the dangerous thing. So this is defined, right? It's defined as one integral going from a to c, right? Fx dx. And we add what it's defined as the sum of the two separate works here. From c to b, minus the sum of these two. So doing this work means we're doing these two separate works. That's what defined as means. Provided the two limits, the two integrals exist. Right? Provided both integral from a to c as an improper, okay, and the other integrals, the improper integrals from c to b, that same function. Converge. Right. Third definition. So in that case, let's look into an example here. So your integration integral is from negative 1 to 1. Everybody else with me on that? But then now we realize that this function has a discontinuity at x equals 0, right? Inside of your integration interval. And so, to state it out, 1 over cube root of x, right, has a discontinuity. That x equals 0. That's inside the interval minus 1 to 1. Okay, that's another way of writing it. Set up the inequality format. So now we have to. So in that way right here, doing this work means we have to produce two separate works, right? So the starting integral means the same as this is the starting integral. But it means the same as two separate improper integrals work. One of them is from minus 1 to 0. One of the cube roots of x dx. Then the other one is from 0 to 1. 1 over cube roots of x dx. So we have to tear down the work, right, and do two separate integral, the improper integral work here. So for the first one, so now we're going to consider individually. The first one here minus 1 to 0, right? Sort of like extra practice for us here. See what I mean? This one here is the same as, see, we got to, now I don't have to beat around the bush anymore. I'm going to create the limits for t, right, going to 0, but from the left-hand side, right? And here we're looking at the integral from a 1 to t, right, 1 over the cube roots of x dx. And the integral itself is quite easy, so I don't think we need to get on a separate the space to do the scratch work or anything like that. So in the next step, right, it becomes just simply what it's a we have right times x to the 2/3. And we are evaluating from -1 to t. Everybody with me? And letting t limits go to 0 left hand side. So that will one more thing. Now next step will become the limits for t goes to 0 from the left hand side. What we're looking at, we have right substituting t into your function t to the 2/3 power minus the cube of the we have right times -1 to the 2/3 power as well. And I made my arguments earlier that hey, this -1 right the 2/3 power really was a positive one right, and it multiplied with a -2/3 here. So one more step, we're going to be looking at the limits for t go to 0 from the left hand side. We're going to 3/2 t to the 2/3, but minus 3/2 here. And that term here, basic limit laws allow you to see that that term goes to simply just 0, right? It's the power on a t, which is the power on a simple t. Okay. So now we're looking at just minus 3/2. So this first one right here is conversion one, right? So that means you're gonna have to advance the next one to the other piece. Okay? You know what I'm saying? Because you got the first one done, right? We put a check mark there. But that now means we have to proceed on the next one. So in the next one here, my integral here is from 0 to 1, right? 1 over cube roots of x dx. And so working through with this one right here, we're talking about it's a limits work. This time I'm going to let s go to 0 from the right hand side, right? Your integral here from s to 1. 1 over root of x. So now in that case, it becomes limits. S gets to 0 from the right hand side. We are looking at now my integral is we have right x to the 2/3 power integrate. And I'm going to be evaluating it from s to 1. So that now will make it work. S 0 from the right hand side. And we have times 1 to the 2/3 power minus we have s right to the 2/3 power. So this limit work will come out. So that's the 3/2, right? That goes to a 0, right? So the whole limit working will turn into a positive 3/2. It's another convergence one. So this first one here is convergent. And this bottom one here is also, this next one here is also convergent. So now, see, you got to look at the definition here a little more closely right here. But the definition says it really as a logic right here, we can only add them up, right? That answer right here can only be added up only when you have verified that both of these converges and come to some limits. If one of them fails you here, you're going to stop right there and say, hey, the overall one diverges. See what I'm saying? No, that's the idea right there. And so now I'm going to say that we're able to find a final. So that means from this, right? The final work here, the final integral from -1 to 1, right? 1 over the cube roots of x here, dx. That answer will be the sum of the minus 3/2 plus 3/2, okay, which comes out equal 1. Right? And then that's here leads to this integral over here is a convergent one as well, the final one. So like that. So yes, you can also add it to your definition here, a little extra line here that says the integral a to b, right, in the same category here is convergence, or it's said to be otherwise, that's how it's. That's how it is. That's the reason why just now, right? Is because both of our two separate improper integrals here turn into two separate convergent values. Right? That's why the final one here is a convergent one, and we can further calculate the final value by summing up the two convergent, the separate values. Okay. So, well, let's look at another one here. Okay. Go ahead and spend some time writing it down. Got a problem written down? And so just like that, this function with you 1 over x minus 1 right, has a discontinuity. X equals 0, right? That, oops, I'm wrong. X equals 1, right? That's inside interval from 0 to 2. That's the problem. Right? So now, this interval from 0 to 2 has to be, the way of doing that is defined as two separate work. One work is from 0 to 1 here, right? That's the problem. X minus 1 plus, if it works, right? If it may work, if it can work, from 1 to 2 here, from 1 over x minus 1. Two separate intervals. So in that case, again, we're going to just repeat our understanding on two separate improper intervals here, where one end of the integration interval is discontinuous, right? And so on this one right here, I'm going to think about, well, that's interval from 0 to 1, or x minus 1. We can do that as a limits problem, where we're letting t goes to 1, right, from the left-hand side of that, right, 0 to t, 1 over x minus 1, dx. At this time of the quarter where we've gone pretty far, right? And you guys should be fast enough with this. You can do a little u substitution for the x minus 1 right here, but I don't think there's a need for that. So it's really just natural log of the x minus 1 in absolute value. Right? And then we're integrating from 0 to t. Really take the limits as t approaching 1 on the left-hand side. So the work here will come out. That's why it's extremely important. We go logarithms of absolute value with it. It's now when you're substituting 0 into your function, you're going to look at it's a natural log of in absolute value t minus 1, and then we're subtracting the natural log of 0 minus 1 in absolute value, right? And this right here, I'm going to take the limits. Then t get close to 1, right, from the left-hand side. Okay. And so this term here, needless to say, right, it comes down 0. So you want to say, no? What about that term then? The logarithm of t minus 1, think about the t axis is here, 1 is here, right? So we have, let's put 1 here, then 2 is here, right? Then it goes like this. And then this function here is a little strange in the sense that it also has another portion of that as well. Because here we essentially want to take those values from t, we get close to 1 from the negative side, but from the left-hand side, so we also have another piece of graph going that way. You know what I'm saying? Okay, so now we don't need to concern about the other piece, but now for this piece right here, as t gets close to 1 from the left-hand side here, it drops down to negative infinity, right? So you have an infinite, so minus infinity. So this series of yours divergent. I mean, this integral of yours is divergent. Just that left piece, right? But you already found is divergent. Now the question is, do you need to proceed to the other piece here? We don't have to, right? We don't have to. Because the definition here is saying It's going to be convergent if both convergent, but now as long as one of these two diverges, right? As long as one of these two diverges, then you can just say that the overall integral is divergent. Because there won't be any answer to add or anything like that, right? So that's why now you can just get back on that problem right there and say, final conclusion. This integral from from 0 to 2, right? 1 over x minus 1 dx. This one here is a divergence. Say no. Okay. So as far as improper integrals, we're pretty much good for that, right? So with these examples right here, I mostly stick with the straightforward evaluation. You know what I'm saying? But before you guys, before we completely close this down here, some of the problems it may say this as follows. It may say this in some of the problems that you're going to be doing here throughout a lot of textbooks or throughout your assignments. There's some problems worded as follows: determine or decide whether the improper integral, right? The improper integral converges, right? Or diverges. See what I'm saying? It's stating that. And then from that way right here, it seems a little abstract. If convergent, right? Find its value. See what I'm saying? I'll find the value of your given integral, your given improper integral, or something like that. So I gotta make clear one thing. At our level of our learning, of course, you gotta admit that we are very beginning into this, right? And so if you were at a much more advanced course, there is a way to determine whether the improper integral converges or diverges without going through taking the limit. See what I'm saying? So basically, I'm talking about, because it makes sense that way that, hey, if convergent, then we're going to find its value, right? So that means finding the value has to come after deciding whether convergence or not, right? It's logically making sense that way. But of course, at our level here, a lot of time a problem like this is being used loosely, and it means it's kind of like I said, we just go ahead and get straight into evaluating it, right? Get some value, and then the evaluation process that will also help you determine whether it's convergent or divergent. And then if any of you have some real good passion for math and decide to later on take a formal math major course in analysis, right? There will be technique for you that, hey, before even doing the evaluation process, before firing up the limits to find the limits, you have ways to prove that the limits will exist before you spend your time finding the limits. See what I'm saying? So when it comes to a higher course, then the logic here makes better sense. But right now, anytime you see this problem, we treat that just like any of the examples we've done. Okay, we just the process that we're calculating those limits will be the one that tells you whether it's convergent or not. Okay, and then if it's convergent, just simply enter that final value into whatever the software that you guys have. That's all. Okay, at our beginning level. Okay.